Ln, or rather LP in our case, we say they will reach equilibrium earlier than reaching to the H. If otherwise, we'll have to find at that L dash how many carriers are available. So this is a problem which we want to solve quickly, and we write now that since we are putting light, there is a constant generation going on there. As the carriers move, they also recombine. Okay, so there are two mechanisms which are shown here. Right now we neglect this because nothing is generated here. So this is which term we are talking about? Recombination. This term is because of gradient diffusion. Okay, so the two mechanisms are trying to bring system to equilibrium. That is what it is. You have created a non-equilibrium situation, and now system wants to come back to equilibrium. So which state we are now in? Constant light, constant carrier generation, recombination going on, and carriers are diffusing out. So it is in steady state. So system is in steady state. And because of that we say dPn by dt is 0 is minus 1 upon q. Actually it should be partial, but if you keep writing otherwise, don't worry too much. Plus Pn minus Pno divided by tau p. Oh, this also is opposite charge, so minus. So we say now, this is the diffusion equation, this is the recombination term, and we can solve this equation to get what? P, because our interest is right now how carriers go down to Pno, how carriers go down to Pno. So from this equation, please remember what is Pn? Pn is the carriers which is function of x. Okay. Pno is equilibrium carrier concentrations in entire semiconductor. Since if Pnx exists, dPn by dx exists, therefore gradient is going to be set in, and if the gradient is going to be set in, diffusion will start dominating, okay, or start working. Okay. Is that clear? If Pnx is varying, dPnx dx is consistently there, so therefore diffusion will follow this dJp by dx term. So we start looking for what is the Jp term, diffusion term actually? Minus q dp by dx. I am keeping that n just to caveat that holds in n time. Okay. If I don't do all of that, I can just write P and N normally, but since we are looking for minority carriers, we keep writing they are minority, P's in N. Okay. Okay, so if I have this, what do can I use this equation to substitute something there? I differentiate this, so I get dJp diffusion by dx is minus q dp d2pn by dx square. Is that okay? Just differentiate. Okay. Now, normally, in all our assumptions, we say dp is constant. dp is constant. But in reality, dp may not be as that constant as we thought, because dp is related to mobility. But mobility itself varies with concentration. So obviously dp is also varying with concentration. But in first order of simple thinking, we assume both mu's and d's constant for these evaluations. Is that correct? In reality, the programs, if you write in some kind of software, d also will be a function of x. Okay. However, right now assume that the diffusion constant, the diffusion coefficient is constant. Okay, therefore differential does not take care of that. We just write this term. So if I replace this term here, what do I get? The next equation. So Since this is 0, they both are minus, so I get, and q I can multiply something like this. Okay, keep right now, 1 upon q, then this is minus into q dp d2pn by dx square minus pnx. Of course, x I am writing, it is already defined as function of this tau p. You can see here this will become positive and this will become negative. I can take this tau p term on this side from the denominator, q cancels, so I get dp tau p d2pn by dx square is equal to, or put it minus as it is, pn minus pno equal to, is it okay? What is Pn minus Pno? At any instant of x, Pn minus Pno represents what? Excess carriers. Pno is equilibrium value. How many above? Okay. If I differentiate this, or if I differentiate this, they are same. Okay. Because Pno anyway is constant. Okay. So now, if I do this, then our equation is simple. I call this delta, I call this delta, and then start solving. And if I do solve this simple differential equation, the solution should be d. Okay, one can say. I remember this term then can be replaced by how much? Lp square. You can write at second time. I have a duster, we don't have. Okay. So Lp square, d square delta pn x, so we can write this equal to Lp square delta pn, which is function of x, dx square minus delta pnx. So this is a first, second order simple partial, not even partial, differential equation. And if I solve this equation, the solution, so I to solve this, how many boundary conditions I need? 2 of them, because second order, so I need 2 boundary conditions. So I solve this equation using 2 standard boundary conditions, which I can write here, BCs. But let's see at this, let's show a figure so that it will be much easier to show what I am talking. This is, I now plot P and X, and this I will now use 0. Why? Because excess carriers will go down to 0. Okay. Last time I made mistake, so I am now taking care. It will go to Pno means excess carrier will go to 0. At the time at x is equal to 0 where I am here, what I am going to say is, this excess carrier at x is equal to 0, I say, since I know the generation rate with which carriers are generated, so I say at x is equal to 0, delta Pn 0, we call it delta Pn, which essentially is Pn at 0 minus Pn at 0 minus the equilibrium value. Okay. So this is one condition which I get, one boundary conditions. What should be the second boundary condition? Other side. X, as I say, L dash I said is much longer than the diffusion length possible. So we say at x is equal to infinity, delta Pnx is how much? 0. Far away from this, the impurity concentration should be Pno, which means delta Pnx should be 0. So 2 boundary conditions, simple differential equation. So if I solve this, then can I rub this part now on the top? I should be This equation I don't have to now keep. I write this is our equation which we are solving, and the solution which you should get is delta Pnx, which I have to repeat is Pnx minus Pno equal to delta Pn into e to the power minus x by Lp. From where this I have got it, using those two boundary conditions, I get the solution of this differential equation as delta Pn. You can see from here, if x is equal to 0, excess carriers are delta Pn. If x is equal to infinity, delta Pnx is 0. So it satisfies the boundary condition. So our solution exists in this form. So we may also say in some full form as equal to Pno plus Pnx minus Pno e to the power minus x by Lp. Okay. So how will it look here? Which is the way it should decay? What is the decay? It is decaying exponentially. So this is e to the power minus x by Lp. So what is Lp from here? 66% of that is when the concentration falls, excess carrier goes to its 33% value of the available delta Pn. That's the characteristic length. Beyond that we say, you can see from here, if I put a 66% value of this somewhere here, you are anyway coming closer to Pno. So the stronger term, diffusion term, becomes lower dominance. It is the recombination which will finally take it back to Pno. But in between, both of them are trying to pull it down so that they go to equilibrium value. This is most important. The effect of diffusion as well as recombination is taken care through which term? The diffusion length. dp tau p is Lp square. dp tau p is Lp square. I am taking care of tau p. I am taking care of diffusion in one term which is called diffusion length. So Lp is one of the major parameters in our device design, which is essentially, as I say, for minority carrier, let's say I put like this. If you wish so. This term is going to decide therefore where we will reach the equilibrium or will not reach the equilibrium. Is that clear? In bipolar devices like PN junction diodes or in bipolar transistors, this number is we are controlling. So what we actually, D is constant. So what we control? The lifetime. So controlling L is through lifetime. Can you control lifetime in a material? Is that clear? Add some impurities which acts like flats. So I can control the lifetime, and if I can control the lifetime, I control the diffusion length. So I know the concentration at any age I can now fix by changing that tau. Okay, I say where it will, what concentration at the age I want. Is that correct? This is exactly what bipolar transistors are looking for. As we go ahead, we will see. This is exactly the principle I use there. Okay, that all of them do not decay. So what happens in the base? Okay. That's exactly what we will do in the case. So that issue, that both diffusion as well as recombination is taken care by one single parameter which we call the diffusion length, which is, another thing you should keep, I have not solved so much for holes in p-type. Why? Because their concentration is already high, 10 to the power 15, 16, and this delta will be smaller than that. So additional term which you are getting in excess carrier is small enough to go to this p is a p0, and therefore not that it doesn't decay, it still has to decay, but that is not so very, because the gradient is very low. So the current coming from the whole decay is present, don't think it is negligible, is not there. But it is much smaller because dP by dx is much smaller, and therefore diffusion term occurring due to the whole diffusion is not that stronger as compared to the minority electron carriers, because they change from much larger value to much smaller value, creating huge gradients. Is that clear? Therefore, in bipolar devices, we keep telling you, minority carriers dominate the transport is because of this phenomena. Don't think that diffusion is not occurring due to holes. They are occurring because some larger concentration is going to some smaller, so gradient is created. So there is a dPP by dx term available to you, but that creates very small amount of current because this slope is very low. Okay. So if you, actually by physics way you should add that. Is that okay? But in real life we don't add, because we know I am adding, let's say, a current of 1 milliamp, a current of 1 nanoamp. So it is the sixth decimal term which I am going to change, so I say forget it. But it is not that it's not present there. I normally don't show it, doesn't mean it doesn't. It exists, because any gradient, the current, diffusion current will flow. Is that clear to you? So this fact has to be understood, that many times we just neglect as if it doesn't exist. It does exist. Okay. Numerically that number is extremely small compared to the other one, and therefore we neglect them in real writing terms. But if you really want to write all terms, do write. Nothing goes wrong. It will be accurate. Only thing is that accuracy is how much you want to see. Do you want to see a 9 decimal accuracy? If you want, wish, yes. Like your computers have how much accuracy built in also, like 88 value it takes, or double precision it takes, 160 terms it takes. Whichever accuracy you wish, you can always build. But in physics way, both exist. But in number ways, we say only diffusion due to minorities is dominant. So in case of P semiconductor, which will now start dominating? The electrons will start dominating in the diffusion terms. Okay, but please remember, even holes will come accordingly. Okay, so this issue which has to be understood by you, that this excess carrier concentration decay relates time and space to some extent, at least in steady state. We say dN by dt is 0. If not, then you have to solve this full partial differential equation. Left side is a time dependent term, so I must somehow convert that into term which is relatively easily explainable. What is dN by dt, and then solve the equation numerically, which is possible some other day, some other time. In our case, we will assume if I apply voltage, I will not remove here. So what I am doing, I apply and remove. Yes, there is a transient case which will have to be solved with this case. What happens if transient occurs? Okay. As far as steady state is concerned, this is good enough. So we just list them. You can also solve the same differential equation with a boundary condition that at x is equal to infinity, we said if the length is not long enough, we say at a distance of say w, we give that value something which we say at w whatever it is, what kind of functions you will get solution of such equations. Some sin h cos h terms will appear, e to the power some terms will appear, which will give you sin h cos h terms. And then the solution will be according. We will solve this. I am not doing it because in PN junction I will solve that case which actually may occur there. Okay. Why I say it in transistor or PN junction I will do, because the length may be different in PN junctions. The base length will be larger than L, smaller than L. In that case we will find out what happens. Right now just go with it. So maybe before I quit this area, one interesting thing which we did earlier also, but we just re-emphasize the fact, the word we used is Quasi-Fermi levels. What is the word quasi I keep saying? In steady state, only in steady state, system looks it is time invariant. That is d by dt terms are zeros. Which means one can see now, though it is not in thermal equilibrium because carrier concentration is varying, but at every x we can say, okay, I can derive as if what is the number of carriers available to me. Gradient means carriers are changing. So at every instant and every x, I know how much carrier x's I have. So corresponding to that, because carriers are related by n is equal to ni square e to the power ef minus ei, if electrons are used. So I know, okay, though ef is normally, we say constant, but just to say how many additional electrons I have, I say, okay, I will make ef variable now. Okay, and that ef I will say as quasi-Fermi level. Is that so? Ef is a function of essentially x. Ef is a function of, is that point clear? As the concentration of carriers changes, at every x there is some concentration, higher, lower, lower, lower. So if I plot a band diagram, I know for each one, if there is a uniform concentration, ef is constant. If the concentration at every x is varying, ef minus ei must change correspondingly to show the number change. Is that correct? And the change in ef we call it as quasi-Fermi level variations. We don't call it Fermi level because our statistics says only in thermal equilibrium. Since system is not in thermal equilibrium, we cannot call that as Fermi level. But we still want to use Boltzmann's relation, so we said, okay, I will call it quasi and get rid of, because I want to know how many numbers related on the band diagram. So should I show the band diagram? So I will be able to. So here is some equation which we wrote for Boltzmann relation. N is equal to ni e to the power ef minus ei by kt. Then we say, if this is n is constant, but let's say n is a function of x. In the first Boltzmann relation we say n is constant, but now say n is varying, which is a function of x. Then I can write dn by dx. Ni of course is constant, 1 upon kt. What else? E to the power ef minus, or call it efn to make it now, n type this divided by kt into what? def, n will now call it dx minus dei by dx. You need not put n right now, because for generalized case it can be p or n. I just wrote n, so I wrote. Otherwise you should just write ef df by dx for p or n, either case. Okay, so what is it trying to say you? What is this value? Ni by this is same as n. Ni into this is same as n. So we say 1 upon nx by kt into def by, maybe n right now, but as I say. And what is this term? What is this term? Electric field, is that correct? This term is built-in fields. Okay. So if I write this built-in field, which is QEX, okay, so if I get dn by dx, what current I can get? If I have a gradient of carriers, what current I can find? Diffusion current, qj 1 upon q djn by d, sorry, q dn, jn diffusion is plus q dn by dx. Okay. Since I know dn by dx, I can say I know the diffusion current occurring because of this. So now, from there, can you guess something is happening? That the Fermi level in thermal equilibrium, how much will be df by dx? 0. Fermi level is constant. So if the current starts flowing, the Fermi level is not constant. Is that point clear? Using quasi-Fermi level theory, we say if the quasi-Fermi level has a gradient df by dx, which means there is a diffusion term flowing in the system. Is that clear to you? Is that point clear? If the gradient, diffusion will occur and the current will be then will show as its equivalent Fermi level is no more constant. So change in Fermi level in x direction in a way represents presence of current, diffusion current. Is that correct? If I want to show on band diagram whether it has a current flowing or not, I will say EF must be a gradient on that, which shows that current is flowing in this device. Is that clear? So someday if I have to represent the real life situation on a band diagram, I am now trying to see, can I see a band diagram and see whether currents are flowing, or given like this, can I see how the current is actually changing? Is that clear? This is a representation which is very relevant. The net current, I will not solve it fully, I will just write down for you. The net Jn current is Q mu n x Ex. Since I have not applied field, this is only built-in voltage or built-in fields plus Q dn by dx. I have already taken Ex here. If I substitute this and this two terms here, what you are going to get is the following: Q mu n nx d by dx of EFN by Q. D is replaced by what? Kt by Q mu. So I substitute this term here. Ex will cancel and this term will occur. What is this term? Sigma x. Please remember this is variable. Okay. So we say sigma nx times, and what is Ef by Q? If I put a minus sign for n type, voltage. Okay. So it's called Fermi potential, where Q phi n is EFN, where phi n is called Fermi potential. Is that word Fermi potential clear? E by Q is voltage, energy by this is voltage, E is QV, electron minus charge. So Q phi, instead of E by Q I can write Fermi potential. So variation in Fermi potential is related to the net current and also the conductivity term, which is function of x. Is that, which is function of x. This fact has to be understood because we are looking for J and x. It is also a function of x. This term J and x is minus sigma n. Similarly, you can write signs correctly for P material and derive JPX. Signs will change correspondingly. And you can see, so now think of it what I am doing. Why I am doing all this? I am going to get, we will discuss later. If you have a PN junction, you have both holes and electrons close by. They are diffusing other way actually. So when they go from one way to the other, because of the process of diffusion, as we shall say then, what will be differentiating between the two regions? Phi n and phi p, because hole will change on the n side and p will change on the n side, n will change on the p side. So phi n and phi p will shift on the either side, and this shift is what we are going to say is because of applied voltage which will apply. Okay. So anytime I see the Fermi level shifts, I say, oh, this must be voltage dependent phenomena. Okay. So I like to connect this variation in Fermi levels or Fermi potentials. Potential means potential difference. Potential difference is nothing but voltage difference. So we say if anything happens because of the voltage difference, essentially there must be some diffusion must have occurred. Okay. Otherwise this could not have occurred to us. This is what we'll now go ahead and prove this happens in actual PN junctions. Okay. This theory is, all that we are doing is for what? Because we want to finally, I tell you, at the end of the day, I am looking for this device. How does it give my IV characteristics? That is all that I am looking into, or plus minus. I am only looking into IV regions of this, and if I want to see that, I see, okay, diode can be made out of a PN junction, and if it has to be made out of PN junction, I must know how the transport occurs. So I am trying to look into all possible transport mechanisms and then say, okay, now I understood how semiconductor transport occurs. For every device, then I'll start actually applying that and say, okay, this is the current, this is related to voltage this way. This is what exactly ultimate aim for us. Once we do this, in a circuit I cannot always use this, so I would like to connect something, this relationship. Maybe this, or I don't know whether this. I don't know what kind of equivalence I can create for a diode. Okay, I don't want to right now say which one or what. Some kind of equivalent circuit I like to create at the end, because for the circuit person can't care whether the arrow is this or each wants equivalent RCs. Okay, if I can create at the end of the day for any device its equivalent, for as far as we are concerned in a circuit, I replace that device by that equivalent and then thank God for it and solve this network normally. Okay. So ultimately, to get this equivalence of this, how much will this be varying, whether this be varying, whether not varying, I like to know, and to do this, I'll use this. Is that clear? So this connection I keep showing you, otherwise you should not feel I am so keen to do only device physics. No, ultimately I am only looking for my circuit. Okay, and to do that, because as I keep telling you, we are not the people who should say that someone will give systems and I'll use it, because then I don't need to be in IIT. That's what I thought so. So for you, I expect that you will tell this is a new circuit, it can do this which no one has done earlier. And to do this, you must know everything then, because then only you can create something which is different. Yes, excuse. So it's still built in. There is no electric voltage applied. Right now, what did I say? The thermal equilibrium situation is contrarily accepted by saying EFN. Okay, that's what we said. We kept saying that in steady state, the system is not in thermal equilibrium. But to say that any instant of x, I say I have a Fermi level, which is not really a Fermi level, but it does give me Boltzmann relation evaluation. So then the field at that point is, I can say, as if built in at that point. So that's why E also is varying along the line. So built-in field is also changing with x. That's what I say, it is x. Okay. That's why it is Ex. Okay. So this is what you said is correct, that the solution there, that's why I say I am use my thermal Boltzmann relationship, but I know I am not correct. But that's why I say quasi. Okay. I am not saying Fermi level, so I say quasi. And using this, then numerically I can figure out, and that number matches with the measure value, so I am good enough to say I am right. Okay, though physically it doesn't sound me well, because I am actually violating the statistics. Okay, yes. We'll show you that. That I'm right now only telling to relate it. So when I show you PN junction, I'll show you what I meant. Okay, just wait. I think I have preempted you for nothing. Okay. Something which I did not do last time, I went home and checked it, that I think I did not put those things properly. Though I said you something that day, but I think I should quickly derive or at least write down that expression. This is something to do because, as I just now said, lifetime has to be controlled in device. That means I must introduce some impurities, some kind of impurities, which will allow me recombinations. Okay. So we said there are, I think, I don't know whether I draw the figures, I did, I think. Is this kind of traps I show you. If this is a neutral, initially neutral, and electrons is captured by this energy level which is close to the conduction band, I say it is electron trap. An energy level which is intrinsically neutral initially, when captures an electrons, okay, then we say it is capture of electrons or electron trap. It will become minus. However, we also said there is a probability if the electrons can be captured by this trap, there is an equal probability that electrons may leave the trap going back to the conduction band. Is that correct? If something is probable to come here, there is a probability it will go back. And in that case, this is called capture. We can do otherwise. Okay, here is our trap level which is negative. Electrons leave this place. It again becomes equal. Then we say it is electron emission. In any equilibrium, the capture rate must be equal to emission rate. The equilibrium system. Capture rate must be same as emission rate. But if there is something we do that the change in capture rate is larger than emission rate, then what will happen? Carriers will be captured, okay, there. And that case, something else may happen. Okay, so we are trying to see in normal equilibrium, thermal equilibrium, capture rate is always equal to the emission rate. Okay, so we say if RCN is the capture rate, that must be equal to REN. For electron traps in thermal equilibrium. In non-thermal equilibrium or non-equilibrium situation, this is an equilibrium. Maybe we can calculate how much is RCN. The capture rate is proportional to what? Can you give me what is the unit of capture rate also? Number per centimeter square per second. This is the capture rate definition. This RCN is proportional to first, therefore we write a constant which is called capture rate constant Cn. Proportional means I put a constant into how much? Available number of traps where carriers can be trapped. If NT is the empty traps, NT is concentration of empty traps. This is number. No, per centimeter square per area. Just I told you that what is capture area. An electron coming here, a sphere of influence, it will see only one plane. The area of that plane is capture area. I repeat, a spherical influence, carrier coming from here will only see this surface. Okay, so it will see only this cross section. Okay, this is proportional to number of available empty traps. NT is available empty traps. It is also proportional to available electrons in the conduction band which can be trapped. Is that correct? Because if there are fewer numbers, fewer can be captured. There are fewer trap levels, even if you have larger number of electrons, all cannot be captured because it will be decided by NT then. And it will also, the probability that this can occur at that level, so call it FT as the distribution function. Probability of capture is decided by availability of carrier being trapped is probable. It's not that every time it will occur. So availability, which is total number may be this, of which how many probably can be trapped is given by the distribution. Okay. So if you write this expression, similarly, can you tell me now how much will be? Okay, how much will be, call it FET, how much will be FET? 1 upon 1 plus e to the power ef minus et by kt. Just write down. I don't have written here, but just write down. This is FTET, okay. Sorry. Yeah, I actually put a minus, okay, fine, you are right. Now this is, this is not that FT actually. This is the distribution function. But how many is available? This is possibility of occupancy. So how much should be actually evaluated? 1 minus these are empty ones. What is the probability said? Occupied. So how many empty? 1 minus is the one which should write there. Instead of FT, it should be 1 minus FT we should write. Is that point clear? This is not correct. This should be something like this. Because these are empty possibilities. Is that correct? Is that point clear? I made wrong intentionally because I want to show that FT is the number which is occupied. So 1 minus FT will be the number which is available for trapping. Is that correct? Probability is the way distribution says so. So if this number we calculate, which is F1 minus FET, then we can also calculate REN, which we now call emission constant. On what it will be, let's say traps are filled now. How many traps will be filled? So let's say NT are the traps which are, all traps have been filled. All of them are filled up, empty. Then, now emission is to get. So what is the probability now I should use? That they are already filled. So NT into FT at ET is the probable that these electrons can emit from the trap levels, which is maximum number NT. So it is not now proportional to N. Why? Because these many carriers are already filled there, they only can emit. So they are not proportional to, at best you can say available states. But available states in conduction bands are much larger, so we don't look for that number now. Because all of them can go there and still there will be states enough. Okay. So this is not proportional to N, whereas in the capture, how many can come will be, I must know how much. Okay. However, in the case of equilibrium, this number is equal to this number. In equilibrium, REN must be equal to RCN. If I do this analysis, I will get something called like this, where N dash, I get the expression for N dash by doing this analysis correctly. Let's just take, I may be wrong because I just now did it some time back in hurry. Check it, must be right. But must be right should be checked. This is just representation. N dash is equivalent concentration, which represents in this form. Okay. This is in what case I talked about? Equilibrium. But in real life what will happen? Let's say capture is more than, why capture will be more? Just now I take a case, diffusion case. I am setting a gradient. So which will start dominating? Recombination. So the recombination terms will actually start larger, then only diffusion can allow that to go to equilibrium concentration. So we say in non-equilibrium, we will get RCN minus REN as the net, maybe I call it for a net recombination rate. Is that point clear? The net recombination has to be larger because otherwise it will not go to equilibrium. Is that correct? The capture must be stronger than the emission, otherwise carriers cannot keep reducing as we are wanting. Okay. So in non-equilibrium case, if I solve this again, those expression once again, you solve yourself. This is given in I think Niemann's book or Sickman's book. I am just reproducing Rn, which is I call it Rn net, is equal for electrons is CnCp Np minus Ni square. Just substitute all that again and solve this. Okay. P dash N dash is similarly written as I wrote here. Okay. How much will be Rn in equilibrium? 0. In equilibrium, are you getting 0 from there? Np is equal to Ni square. As soon as you are in thermal equilibrium, Np is equal to Ni square, Rn goes to 0. So capture rate is equal to emission rate. So this expression now tells that for any material with electrons and holes, excess holes or electrons, the net capture rate will be proportional to this kind of expression. And let's take N semiconductor. This is both of them, valid for both of them. Let's take a material is one kind. For N semiconductor, please take it. N0 will be greater than delta N, which is equal to delta P. Okay. N0 will be greater than P0. Okay. Then we say N0 will be greater than N dash. N0 will be greater than P dash. Okay. Prove yourself, and if I substitute them here, Rn for N type semiconductor is delta P by tau P0, where tau P0 Tp times Nt. So this analysis is given in the book. I want to finish quickly today. Then you can write both expressions and solve. Keep solving. Okay. Okay. Rn is the net capture rate of electrons in P. In N semiconductor. So now I am saying it is N type semiconductors. These are the values. Holes are in the minorities. So decay is essentially hole dependent. The value can be given by 1 upon Cp times Nt. Rn is dP, you can say, if you wish, En by tau Po. This expression is generalized expression for recombination rate. Earlier we have already said delta by tau, which we are getting again, delta by tau. If I substitute all this in that equation, one can solve the same way. Same way for the other semiconductor. So what is it I am trying to say? These are called trap centers. Similar thing you can do for holes. Holes trap will be where? Near valence band. Why? Because then possibility of hole trapping is larger. However, if I want to have a good recombination, I will like both electrons and holes to actually recombine. That's what recombination essentially we are looking for. So where should be the place where both have roughly equal probability? In the mid band. So if I have a traps level somewhere in between, then that level is called recombination center. What is it called? If ET is close to midband base, it is called recombination center. When we say electron is captured, hole is captured, and recombined, please take it. There is very unlikely that hole will travel all the way probability wise and recombine here. So only electron emission and capture can take place. If something is here, only hole and can capture this. In between, there is a probability that hole can be captured and electron can be captured. And if they recombine, we have got a net recombination possible for us. Is that point clear? So what is the difference between normal trap and recombination center? The trap which is in the midband, close to the midband, has larger probability for both sides. Therefore, recombination is stronger. The last word, which materials can do this? The most popular lifetime killer, as I call, is gold. Okay, is gold. Typically, gold gives one level around 0.55, sorry, slightly lower, 0.55 eV, from the conduction band and another trap at 0.34 eV from the valence band. There are two levels for the gold. Which one will have better recombination? One which is closer to 0.55, which will give dominant recombination mechanisms. Now there is something fun we'll see. This is called amphoteric impurity. What does that word can be? No. The acceptor is above and donor is below. This level is a donor level and this level is acceptor level. Normally acceptor level is lower than the donor level, but since the donor level is lower than the acceptor level, these materials are called amphoteric. Okay. The gold is the one which is normally used by us in technology to actually create lower lifetimes. Is that correct? Because then recombination will be stronger, lifetime can be. So what is the advantage of lower lifetime in a device? Speed, very good, she said it, speed. Because the carriers will therefore from one state to other, they will let's say in one case, huge carriers created. When I change the polarity, they should recombine fast because they should go to the other state. So as fast they recombine, I can again switch on. Okay, that means the higher speed circuit should have lower lifetimes. We'll go back and see in transistors. If I do this, my gain will go away. So I'll say how much gain and how much lifetime I should play, so that roughly I can get good at both of them. Okay, see that?